that thing with the surfaces? If y'all have that, you can turn it in, please. Pardon me? Whatever, I only asked for the last two, but you can turn in just the last two or all of them. It doesn't matter to me. Just make sure your name is on whatever you turn in. Now that is something, Josh, that you'll have to work on. Your name. Okay. All right, so what we were talking about last time was coming up with ways to represent surfaces using vector functions, right? And we spent most of the class looking at some of the basic surfaces, disks, cylinders, planes, and we came up with different parametric functions for, or vector functions for those. Now we're actually going to go and continue this section and hopefully get into the next section, hopefully get through as much of 3.7 as I possibly can. Right there is fine. But I did promise you a summary of the formulas for Chapter 13. So I have those. These are designed only to be a reference. They are in no way, shape, or form something that I would publish to be put out there, you know. It's just for a student who's been in my class who wants to be able to look at all the formulas in one place. So if there's a theorem, let me give you an example of what I'm saying. Okay, just flip to, let's see, flip to the third page, the back of the third page where it says fundamental theorem of line integrals. It says line integral over C of gradient of f dot dr equals f of rb minus f of ra. I don't even explain what R is here, right? I mean, like, what's R? Well, R is your curve, right? So, I mean, there's things that are left out, conditions that are left out, but if all conditions are met, that's the fundamental theorem of line integral. So just, it's a summary. That's all it is. So we've done a lot of this, but, well, I even have, like, common parametric surfaces on here, cylinders and spheres and things like that. So, you know, do what you want with this. You can use that. I don't mind if you use that on the final. Well, it depends on what you write, you know. If you want to add some formulas to it, that's okay, but you just can't go working out a bunch of problems on it. All right, so let's continue. We had the surface. Last thing we did was we looked at, like, the sphere, right? So there's a surface. And now we talk about derivatives, right? So the geometric meaning of derivatives of vector functions. Remember from vector functions of a single variable, when we looked at the derivative, so here was R of t here is this bluish curve, right? That's our vector curve. And the derivative was the vector, right? It was a vector, the red vector, which gave us like an instantaneous direction and magnitude at every point on the curve. That was what r prime of t represented, a vector. It was tangent to our curve, right? So that was the geometric meaning of the derivative of a vector curve. So what is the geometric meaning of a vector function of two variables? Right? So now you have, remember, vector function two variables draws a surface. So what does the derivative represent? Well, what we'll have to do is we'll have to, just kind of like we did when we had functions of two variables, we will have to hold one variable constant. If you're just coming in, you can turn in your stuff if you have it. I couldn't open your attachment. What file format was that? Journal? Yeah. Yeah, no, I didn't. Will it open with OneNote? It should. Can you save as PDF? Okay. If you get time, can you send it as a PDF? I'll try and open it, but just in case, because what I'll most likely do is print it out anyway. So, okay. I replied to you. I said I didn't know if I should open this or if this is a virus because I didn't know if you meant to send it. Like it could have been some, I'm not saying you sent me a virus, but you know what I'm saying. Someone hacked into Canvas and is sending everybody viruses. So I just didn't even open it because I wasn't familiar with the extension on that file. Okay, so what we'll do is we'll hold one variable constant. If we hold one variable constant, remember what we got was what was called the grid curve. It was just one curve on the surface. And if we have a single curve on the surface, then we can talk about a tangent vector just like we did before with one variable, right? And then we hold the other one constant and do the same thing. So visually, here's what we have. We pick some point on our surface. In this case, we're using the sphere, right? We pick some point on that surface, and there are some, I don't have my grid ones here. Let me see. Okay, yeah, there are my grid lines, right? So if I hold one of my variables constant, I drew these circles. If I hold the other one constant, I draw these other circles, right? So if I, now let's just hold one of them constant. So look, what I've done now is what we're going to call the partial derivative of r with respect to u. So I'm holding v constant and letting r be the, r of u be like the curve function. So when I do that, the derivative there is this green vector. Make sense? And then the other partial would be holding u constant, and that means we'll get this red circle here. And so the tangent vector is this red one. Everyone see that? Does anyone see where we're headed with this? We have two vectors that are orthogonal in this case, right? But I have two vectors. What do we always like to create if we have two vectors? What can we create from two vectors and a point? A plane, right? I mean, do you see that this surface has what we would consider to be like a tangent plane? So instead of having tangent lines on a curve, we're going to have tangent planes on a surface. But to construct it, we need two tangent vectors. And then from that, cross and get the normal and all that. That's where we're headed. But let's just see. Let me see here if there's anything else. No, that's it. If r of u is the vector which is tangent to the space curve, r of u where v is held constant. So same definitions that we had before. So straight from this, I would like for us to do the following. Well, I guess the example's coming. Let me get these out of here so you can. So here are our two vectors. From those two vectors, we can create a plane, and then that is our tangent plane. Our plane, it does depend on where we are, right? If we change, of course, our value of u and v, our plane is going to be different, you know. So the equation of our plane should be dependent on the point at which we're on, the point on the surface, right? So our first example here is to find the equation of the plane tangent to the unit sphere at the point root 2 over 2, 0, root 2 over 2. So geometrically, where is it? We're trying to find this plane right here. There's a point on the curve. I mean, there's a point on the surface, and we're trying to find that tangent plane. Questions as far as what we're trying to do? All right, so first thing I need to do is maybe remember what it is that I need for the equation of a plane. For a plane, what do I need for the equation of a plane? For a plane, I need a point, and I need the normal vector, right? The normal vector, we called that the vector ABC, right? The point, we called that x naught, y naught, z naught. And then from that, the equation was A, x minus x naught, plus B, y minus y naught, plus C, z minus z naught equals 0. So that's the equation of a general plane, right? Did that way back in first chapter. So the vector, the normal vector, like we said, should come from those two tangent vectors being crossed. So I'll need to get those, right? Those two tangent vectors. And then the point is already given to me in the problem, isn't it? Root 2 over 2, 0, root 2 over 2. So all I need is really to get that normal vector. Where does it come from? Where do those derivatives come from? They come from a vector curve, right? A vector function that draws the surface. So I need to come up with what draws the unit sphere. What vector function? So you cannot use the equation of a sphere here. You have to use the vector equation of the sphere. So it's going to require two parameters, u and v. And I believe we did this last class, didn't we? Pretty sure we did. Let's see. It's where we motivated the whole thing. As a first example, I said, do you recognize this, right? We said that this draws the sphere. And I said that this was the unit sphere because the row in front of these was 1. Right? We had talked about spherical coordinates and how you go from Cartesian to spherical. You replace x with rho, sine phi, right? Sine phi, cosine theta, things like that, right? Actually, yes. But this is the conversion over using u and v instead of phi and theta, and rho being fixed at 1. Y'all following this? So this is the actual curve we're going to use. This is it. So sine u cosine v, sine u sine v, cosine u. So I'm going to write that down over here now. My surface is generated by this. Where u is between 0 and pi, and v is between 0 and 2 pi. That draws the sphere, the unit sphere. What I need to figure out now is what the partial derivative of this with respect to u is. So what we'll do is it's going to create a vector, right? We're going to hold our v and treat our v like it's a constant in the entire vector function. So when I do a derivative of a vector, I do derivative of each component, right? That's what we did when we had just t in there. So this will create a new vector. What is the derivative of sine u cosine v with respect to u? What will this be? So cosine v is a constant, right? So just ignore it for now. Derivative of cosine u, sine u is cosine u, right? So this becomes cosine u, cosine v. Then, derivative of the next component with respect to u. Cosine u, sine v. And finally, derivative of cosine u is negative sine u. Yes? Okay. Next thing, I need the partial of r with respect to v, which would be, so go through it again, treating your u like a constant this time. You should get, what's your first component? Negative sine u sine v. You could go either way with that, right? And then, derivative of the middle component with respect to v, sine u cosine u. Cosine v. And then finally, derivative of cosine u with respect to v is 0 because it's a constant. All right, now that is the general formula for the tangent vectors, right? In order for me to figure out the specific vector on my plane, don't I need to know the u and the v? I mean, don't I need to know exactly where I am on the sphere? This is a little bit of a challenge. How am I going to figure out what U and V are that I plug in here? How do I get that? How do you mean? To the coordinates? What do we have? Where are, okay, so you're using the fact that we are at this point, right? So my original vector function, which is r of uv, I need to figure out what u and what v I plug in here to get to this point. So I need to match up all three components to match up with those three coordinates. So let's start with, let me start with this here. Go ahead. Yes? That's right. That's right. That's right. That's right. Yep. So that, I mean, that's basically the attack we'll use here. But everyone understand what we're trying to do? Because that's the more important thing is, I mean, like, what is it that we're trying to do? We're trying to recover u and v, right? We need to find the u and the v, which gives us this point, root 2 over 2, 0, root 2 over 2. And do we all understand that when you plug in a u and a v, you actually get a vector up there, but that vector points to a point, and that's why we're saying gives us this. We all understand that a point is not the same as a vector, but that vector goes from the origin out to a point, and that's what we're looking for. So matching up the components, I like that idea. We do know that cosine u, this right here, must match this, right? So you tell me now, where is cosine u equal to root 2 over 2? 45 and negative 45, yes? But what's our restriction on u? What's our restriction on u? I got to be between 0 and pi. So depending on how comfortable you are on this, I mean, this is a problem that I would have given on a pre-calc class. I don't know how you look at trig functions, but this is the way I do it. If I want to know where cosine of u is root 2 over 2, and I know my u has to be between 0 and pi, I kill off the bottom two quadrants. I know I've got to find an angle somewhere between here and here, where cosine of that angle is root 2 over 2. And on the unit circle, what you got? You want me to eat that before the test and then I'm going to pass out or something? Oh. Thank you. All right. Okay, so cosine means I'm looking at the x-coordinate on the unit circle. How many of you learned it that way? Right? Yes? How many of you don't know what I'm talking about? It's okay if you don't. Like what the hell? Why is he drawing a circle? Okay, when I'm trying to figure out where cosine of an angle is root 2 over 2, I go to the unit circle and I figure out where the x-coordinate is root 2 over 2. If it were sine of u, I would go look at where the y-coordinate is root 2 over 2. I think that's one of the most efficient ways to find the values of the common trig angles. If you do it by the graph, then, you know, more power to you, but this way I think is just cleaner. So I'm looking for an x-coordinate of root 2 over 2. The only place that happens is at pi over 4. Yes? Pi over 4? I'm going to use radians. So pi over 4 is where that happens. So u must be pi over 4. Now, what else should we match up here? You said go to that middle one, right? This one. Sine u, sine v has to be 0, right? So let me just jot that down real quick. I know that sine u, sine v must be 0, but I already know what sine u is, right? What's sine of u? Well, what's sine of pi over 4? Root 2 over 2? So this really becomes root 2 over 2 sine v equals 0. And I can divide both sides by root 2 over 2. So I really just want to know where sine of v is 0. So I draw a new circle. I usually would say you do this all in your head because you're used to doing it. But sine of v, it's a different angle than u is, right? My restriction on v is between 0 and 2 pi, so I do not kill off any of the quadrants. I want to know where sine is equal to, where sine of something is 0. Sine is the y-coordinate. So where does that happen? Where's the y-coordinate 0? 0 and pi also, right? 0 and pi. And 2 pi. It's actually 3 places. Do you agree? So v could be 0, or it could be pi, or it could be 2 pi. Yes? So which one is it? How do we know it's 2 pi? Okay, so now we come back and we say, well, look, we might need this one to narrow it all down. So we need sine u cosine v to be equal to what? This one? Root 2 over 2? So let's go ahead and put that, let's write that one down. I need sine u, I'm going to put it over here. Sine u cosine v to be equal to root 2 over 2. And now what did we say that sine of u was? We said sine of u was root 2 over 2. So this is saying root 2 over 2 must be equal to, or cosine v must be equal to root 2 over 2, which means that cosine v must be 1, right? Dividing both sides by root 2 over 2. And where's cosine v 1? So again, I'll just draw, well, no, we can kind of tell from here, right? Go back to here, where's cosine 1? At 0 or 2 pi, right? 0 or 2 pi. So, we could use either 0 or 2 pi, right? 0 or 2 pi. So I'm just going to let v be, let's go 0. Now, getting back to what it is we wanted to know, right? We wanted to know these partial derivatives at that specific point, which meant that we need to know u and v, which we just got, right? So now let me go to a new page. So if u is equal to pi over 4 and v is equal to 0, then the partial derivative of u, of r with respect to u, turns out to be what vector? So what you're doing is you're plugging in pi over 4 and 0 in for v, at u and v respectively, into these two, right? That's what we're going to do, into these partials. Okay, so without going through all the work, you should get root 2 over 2, 0, negative root 2 over 2. And then the partial of r with respect to v, at the same point, you should get 0, root 2 over 2, 0. Make sense? So how are we going to, what do we do with this now? I don't want you losing track of what we're doing here. What do we need to do with these two vectors? Cross them, right? Our normal vector that we're looking for, remember, we wanted a normal vector, should be r, partial r with respect to u, cross with partial r with respect to v, which is, you cross those, and y'all remember how to do cross product of vectors, right? You could do it different ways, but I'm going to trust you can get a cross product now. Should I remind you? Because we're going to do it in a second. We aren't going to do it with vectors that have numbers. We're going to do it arbitrarily. You would do like this. Tell me when this starts looking familiar. No? So if I want to know the ith component, I cover up I and I do determinant, right? And then cover up j, do determinant, but then change the signs, and then cover up k, do determinant. Yes? If you do that, you should get I'm getting 1/2, 0, 1/2. So that's your normal vector. So then that's all we needed, right? That's our ABC. And now we can come up with the equation of the plane. The equation of the plane should have been what? So the equation of the plane would be 1/2, then x minus x naught. What's x naught for us? √2/2, right? That's over there. Minus √2/2. And then plus b, which is 0, right? I'm going to put it here just so we can see it all. Y minus y naught, but y naught was 0. And then plus c, which is 1/2 again. And then z minus z naught, which was √2/2 again, equals 0. That's the equation of my plane. Now I could clean it up, but that's it. We're done, right? You can do that for any surface. As long as you can come up with the parametric representation of it, the vector function, as long as you can take partial derivatives of it and cross them, you can do that for any surface. Okay? Questions? Very good point. For a sphere, though, that would only work for a sphere, yes. So this is just to get motivated into the idea, but your normal, yeah, would have just gone from the center out to the point anyway. Yes. Was the point negative? Are you looking at that? You were looking at the partial, yeah. All right. Now, this whole idea, all right, can extend out. Now, think about this. If you're given a surface S, and you have its parametric equation, basically its vector function, where you have some restriction on u and v. So u and v are in the domain of this surface. That means your restrictions on u and v draw this surface. And the surface area of S, the whole surface area, is this. What the hell is this? Well, just look at this little red patch right here, right? So I'm going back to the sphere because it's easy to illustrate. I've got this big sphere. I want to find the surface area of it, right? So let me just focus on trying to find the surface area of that little patch, that red patch. So what I'll do is I'll first come around here. Let me move close to it. All right, do you agree? Let me see what this whole thing is, go small. Oh. Do you agree that that tangent plane, if I find the area of it, isn't even freaking close to the area of that red patch? Right? And if I try and zoom in, and I don't know if I'm going to be able to get that. I've had trouble in the past zooming in on this. It's actually not bad. You can see that our tangent plane, right, obviously is off the surface a little bit. So it's not right on top of that red patch that we're looking for, right? And the red patch has a curve to it. Our plane is flat. But if we go small enough to the infinitesimal, right, then that plane, right, the plane is going to be a closer approximation to that red patch than the error we get with allowing it to be big. Now, what I need to do is I need to scale the area of this plane. So think about what I'm saying. We can find that plane, right? That plane comes from these two vectors. When you have two vectors, you can always find the area. It's the area of the parallelogram formed by two vectors. There was a formula for it way back in the beginning. We can find the area of this green thing, but we need to scale it. And we need to scale it by, well, what does the formula say? How do you find the area of the parallelogram formed by two vectors? You take the magnitude of their cross products. Okay, that's a formula from way back when. If you draw U and V, they form a parallelogram. The area of that parallelogram is magnitude of the cross product of two vectors. Well, look, magnitude of the cross product of the partial derivatives, right, is the cross product of two vectors, magnitude. But we need to scale it so that it will match up with that red patch. So we scale it by what? dA. dA is the infinitesimal rectangle, which would be like du dv, du times dv, because u and v are our variables. And notice it's a double integral, right? So I'm hoping that kind of geometrically convinces you that we can find the area of the surface area of the surface by doing the infinite sum of all of these little patches. And each patch requires that we do a parallelogram and scale it, and then add them all up. Does that seem okay to you? Visually, does it seem okay? All right, so let's do an example. Find the surface area of the unit sphere. Now, if we go into a book, right? If we break out a book, what's the book going to say? If you have a sphere, what the hell? If you have a sphere radius r, the area of the sphere is 4 pi. Anyone know? You're thinking volume squared. You're thinking 4/3 pi r cubed, which is your volume. Y'all have your formula sheets? The book has it, right? In the very back? The first page of the... Right there. Area for it? There we go. Okay. Oh, yeah. Anyone else need the formulas? You came in late. Did you get these? You did? Okay. Okay, so if this is the unit sphere, right, it has a radius of 1, what should our answer be? Just 4 pi, right? 4 pi. So I have a question for you. Let's see how difficult you want this to be. Do you want to do the surface area for the unit sphere, or do you want to go and do it for sphere radius r? Like a general formula. You don't want to try for the radius r? It's going to be a little more challenging, but we can... You want to see it with the 1 first and then do it as a take-home bonus? Yeah, love that. I like that idea too. All right. Basically what you'll be doing is deriving the formula for the surface area of a sphere. That'll be your take-home bonus due next class. But for us, we're just going to do the unit sphere, all right? Keep it simple. Well, the good news is that I actually know the vector function for the unit sphere. We've been using it for the last example, right? It was r of uv is sine u cosine v sine u sine v. God, if I could get this damn thing to stop doing that. Does your tablet do the same thing that mine does, where it always like draws these little lines? It doesn't do that? I might have to look at what program you're using. You said it was like a different one, right? It's the version before this one, but it's OneNote? Okay. I think that annoys the shit out of me, that it always wants to connect lines together just randomly. Well, it seems to be random. I can't seem to figure out the reason. Okay, so this is our surface, right? Be aware that the 1 is right here. Okay? If you were going to do this at home, you would change that 1 to you would change the 1 to like r. And just remember r is a constant throughout the entire problem. Or rho, if you wanted to call it rho. So So what do we need? For the surface area, the area will be equal to the double integral over d of the magnitude of the cross product of the partial derivatives with respect to area. So whenever we did double integrals, right? Double integrals, you needed to know the restriction on both variables. And in our case, we know it, right? It's given to us. That's how we define the sphere. So we are going to be able to get our limits of integration on this, right? What else? Anything else? Well, we have to figure this out, right? This dA is going to turn into like du dv. Subtle question here, and let's see if you catch on to this. This is kind of a bigger picture thing. Do we have to do, you know how when we converted from like Cartesian to polar, we had to always put the r in there? Remember that? And when we went to Cartesian to spherical, we had to put something weird in there? Do we have to concern ourselves with that here or not? That's right. We are not changing coordinate systems at all. Our coordinate system is actually our vector function, right? Our vector function is our vector function. It didn't come from Cartesian. Like, we didn't start the problem in Cartesian, now we're going to spherical coordinates. That's not what happened. We drew a surface with the vector function. That's what we did, right? So we do not have to incorporate that thing. I hope that makes sense. When we plug everything into this formula, everything should work out. We don't need any Jacobian determinant little thing to pop out. All right, but we do need to compute this cross product, which is going to kind of suck. So we did the partials earlier, right? Didn't we? So I'm going to write them down. Well, you know what? I might cheat. I might come over here and steal them. No, previous page right here. They're all crap. I'll just write them down. So what is r, partial r with respect to u? It was cosine u, cosine v, cosine, damn it, cosine u sine v, negative sine u. And then the partial of r with respect to v was negative sine u, sine v, sine u, cosine v, 0. Now, I need to cross product those, right? And notice also I'm not plugging in that point anymore, right? I'm not trying to figure out what my angle is because I'm not at a specific point. I'm trying to find the surface area of the whole thing. So I have to cross these as is. So I wrote them this way because it would be easiest for us to do the cross product. If I just kind of throw my I, J, K up above it, I can just do my cross product right here. So my cross product, r, partial r with respect to u, cross partial r with respect to v, will be a vector. The first component is cover up the I and do your little determinant here. So what do you get? 0, right? Take away a negative, so add what? Sine squared u cosine v? Sine squared u cosine v. All right, now let's get our j component. Bless you. So I do this one times this one, which is 0 again. This times this, which turns out to be a positive, but I'm subtracting it. But then I'm subtracting it. What is it? Plus, right? It's positive. Yeah, no, it's okay. It gets a little confusing. Some people say that when you get to j, you just do it the other way. And so either way, it should be plus whatever this times this is, which is what? Sine u squared again, and then what? Sine v? Now I need my kth component, which is going to be these two multiplied minus these two, but it's a negative, so plus, so it's this plus these two, right? Without the negative there. So what is this? What is this times this going to be? Cosine v squared, and then sine u cosine u? But then what? Minus, I've lost myself here. Minus, but then it's negative, so plus this times this, which will be sine v squared and then cosine u sine u. Are we all together here? You see, it's kind of nice in here, right? This is going to turn out to be somewhat nice, because what can I factor out of both of these? Factor out a cosine u sine u from both of these. If you pull a cosine u sine u out, you're left with cosine squared v plus sine squared v, which is 1, right? So this is just going to turn into that. That just makes it a little nicer. This is still the same, right? Okay, that's the cross product. Now what we need is the magnitude, right? The magnitude of the cross product. So the magnitude of the cross product will be, pardon? Is there what? Depends on your calculator. Yeah, I mean, like you could program it onto. I'm thinking most of the graphing calculators that allow you to write programs, you could do it. I'm wondering how it would handle arbitrary values like U and V. I think the TI-89 will do it, and the TI-Nspire will do it because it can do algebraic manipulation. But I don't know about anything under that. Yeah, because this is a little tedious, right? All right, so now it's what? Square root of the sum of the components squared, right? So you have to square each of these components and add them up. So square this one, and now that becomes sine u to the 4th cosine squared v, plus the next one, which is now sine u to the 4th sine squared v, and then plus the last one, which is now cosine squared u sine squared u. Everybody agree with that? See anything we can do here? Yep. These two both have sine u to the 4th, or sine to the 4th u, right? So I can factor that out. What would I be left with if I factor that out of just these? So if I pull this one out, and I pull this out, what I'm left with is cosine squared v plus sine squared v, which is 1. So this just becomes square root sine to the 4th u, or sine u to the 4th, and then what's left? Plus cosine squared u sine squared u. What can you do here? Factor sine squared out, and you'd be left with sine squared u plus cosine squared u again, right? Which is 1. So this is just the square root of sine squared u, which is just sine u. Absolute value. Yeah. The thing is, you go back to your restriction on u. U is between 0 and pi, so you don't have to worry about it being negative. Make sense? So we don't need the absolute value. That's a little subtlety here. All right, so now to the integral. We want the double integral over d of the magnitude of the cross product of the partial derivative vectors. So that just came out to be sine u, right? dA. So let's just now replace our d and our dA with what they are. I'm going to go integral, double integral. I'm going to go sine u. Now, does it matter if I go du or dv, which order here? It does not matter because they're both between two constants, right? So my outer one, v was restricted between 0 to pi. U was restricted between 0 pi. And that should be a pretty simple antiderivative, right? Do the inner one, what's the antiderivative of sine u? Negative cosine u. Evaluated at 0 and pi. When we evaluate cosine u at pi, we get -1, but then it's negative, so that's 1. And then when we evaluate it at 0, we get 1, but it's -1, but then we're minusing it. So this all comes out to be a 2 in there, okay? So we want the antiderivative of 2dv, which is just 2v evaluated from 0 to 2 pi, which is just 4 pi. Which matches what we said it would be. We good? Not really. I mean, it wasn't given in the problem, but when we first defined this, when we were talking spherical coordinates, we said that we have two variables. We have a phi variable, right, which started straight up and was allowed to go down and then come through to pi, so 0 to pi, and then our theta variable was the rotation this way was allowed to go from 0 to 2 pi, and then our rho was back and forth. So when we converted over, what we've done here is we've replaced the phi with u, and we've replaced the theta with v. So it's the same coordinate system, the spherical coordinate system, but replacing the theta and the phi. Am I answering your question? So it's implied because we're drawing a sphere. Now, on a different problem, you're going to have to figure it out, which I think I have a different problem here now. Well, no, this is just something a little different. So we right now have a very powerful tool in the toolbox. If we can come up with a surface, a vector equation for a surface, we can find its surface area so long as we can actually compute the magnitude of the cross products of those partials. That can be trouble sometimes. But if we can do that, we should be able to find the surface area. Now, in the special case where your vector equation is actually just our standard function of two variables, meaning, remember when we were first studying functions of two variables, we said, okay, what happens is you plug in an x, you plug in a y, and it gives you a z, and then you put all those together and you create this surface, right, where the domain is the ground. Yes? So if we define a vector function that way, in other words, we let our x, the parametric equations for x, y, and z be the following things. Let x just be whatever you want it to be. So let it be like x. In this case, I'm going to say call it u instead of x. Let our y component be just v, which was like the y. And then let our z be a function of those two. Then this behaves just like our standard surface. I guess what you're not seeing in this is I'm getting confused looks. What I'm doing is I'm saying this. I'm defining a vector function to be where the u is just u. That means, sorry, the first component is just u. The second component is v. And then my third component, z, is some function of those two. What I'm claiming to you is that this right here is basically the same thing as this, f of xy, right? It's going to draw the same exact surface. Or if you'd like, it's f of uv. Replacing x with u and y with v, that up there would draw the exact same thing as this. Are y'all following that? So if you're given a surface, if you're actually given z as a function of x and y, then this magnitude of this cross product thing will turn into this, which is the square root of 1 plus partial of f with respect to x squared, partial of f with respect to y squared. And I put out there, why is that true? So let's talk about it. Why in this special case would this magnitude of this cross product, which I think all agree is probably the hardest part of the problem, right, is computing that, turns into something like this, which is pretty simple. So let's convince ourselves why that's true. Go back to this. If I say find the magnitude or partial of r with respect to u here, what would you get? With respect to u, 1, 0, right? And then whatever the partial of z with respect to u is. I don't know that, do I? And then over here, what's the partial of r with respect to v? That would be 0, 1, and then whatever the partial of z with respect to v is. Following? Now, if I say take the cross product, then you do your little game here, right? Cover up the eyes. When I do this and this, what do I get? 0. You get negative partial z with respect to u. And then do the middle one, so we get what? Here and then here, but then change it. So negative partial z with respect to v, and then what's the last one? 1 and then nothing, so 1, like that. And now find the magnitude. See, wasn't that cross product pretty simple? The magnitude is the square root of each of those squared. So I'm going to put the 1 first. Then this is the partial of z with respect to u, right? I'm going to write it with a different notation. And when you square it, the negative doesn't matter anymore. Partial z with respect to u, right? Squaring is going to take care of the negative, so who cares about it? Plus the next one is partial z with respect to what? V squared. Y'all following this? And so that's where this formula is coming from. What we're saying is that if you are doing this special case where your z is a function of x and y, then don't worry about this. It always is going to become this. So all you're going to have to be able to do is take a couple of partials of that function, you're good. And then plug it in this formula. And then the rest of it's the same. Look, right? Double integral dA, square root of this, dA, for x and y in D. So we're switching back to x and y instead of u and v. I hope that makes sense. Does it or not? Yeah? Getting some nods of approval. I'll go with nods. That's okay with me. It's better than nothing. So check this one out. This is a great problem. Find the surface area of the part of the paraboloid z equals y squared minus x squared, which lies between the cylinders x squared plus y squared equals 1 and x squared plus y squared equals 9. So this is, I'm not going to show you the picture yet. All right. Find the surface area of the part of a paraboloid. So a paraboloid, this one right here, what does this look like? Like in one direction, it looks like a parabola like this, right? Like if x is 0, it looks like a parabola that opens up. But if y is 0, it looks like a parabola that opens down. So this is a surface, right? It is a function of two variables. This is like our f of x, y. So it's like the saddle. Remember the saddle? In one direction it's down, the other direction it's up. So this is like a saddle. And I'm trying to find the surface area of this saddle, but I'm only looking between these two cylinders. Now, this first cylinder opens up parallel to the z-axis, has a radius of 1. So again, we have that saddle, right? We have a cylinder coming up through it, and then we have another cylinder coming up that has a wider radius. So I'm looking for the surface area of that saddle between those two cylinders. Is that what you were thinking? Yeah, you know, I mean, were you? I don't know. See, you're going to have to somehow extrapolate that idea from the picture, from the just what's given. So you have your saddle, right? You're trying to find the surface area of that thing between the two cylinders. So the first cylinder's on the inside, it basically cut a hole out the middle, and then the outside cylinder. we look at it from the top, now you can see you have your inner cylinder and your outer cylinder, right? You're looking for the surface area of that other one between those two. Does that all make sense now? Got it visually? All right. Well, this is a special case. The special case is that the surface, right, that we're trying to look at, z equals x, y squared minus x squared, is a function of x and y, right? It's a function of x and y. So let me get to work on this. You know, I just recently figured out how that works. You know what I'm talking about on Windows, anyone who uses Windows, that when you move it to the side, you get it to go halfway automatically? Yes? Have y'all seen that? Anyway, I used to think that you just had to like throw it over there. And like I kept on trying to do it. I was like, man, how do I get that shit to work? But yeah, all you do is drag it till your mouse hits the edge, and then it automatically you drag, click and hold, and drag to the edge. So I'm sitting there trying to throw it, and sometimes it would work. And I'd be like, how did it work that time? And it would be because my mouse actually got to the edge before I let go. Oh, anyway, stupid. All right, now I'm in that special case, so here we go. We have that z is a function of x and y, which is y squared minus x squared. Which means if I want to take this double integral over d of RU cross RV dA, which is the surface area, right? What I need to do is just convert that over to, that becomes the double integral over d of what? Square root of 1 plus the partial of f with respect to x squared plus the partial of f with respect to y squared dA. So let's talk about some partials because we'll need them. What's the partial of f with respect to x? 2x. What's the partial of f with respect to y? Wait, that was negative 2x, wasn't it? And then 2y. If I square those, right, I'm just going to get, what, 4x squared and 4y squared? So let's plug those in here, and here's where we'll be. Double integral over d of the square root of 1 plus 4x squared plus 4y squared dA. Any questions? So far, things look pretty okay. Eh? So now let me ask you, what's my region D? Because I need to come up with limits of integration, don't I? Let me come up with limits of integration. And then change my dA to like d something, d something. Well, we are in terms of x and y, aren't we? Is it dx? Well, it could be, yes. It could be dx dy. That's no problem. We can make this dx dy. Or dy dx. I don't know. But if that's the case, then you need to be able to define the region D in terms of x and y. So what is our region D? What is the region we are integrating over? Well, that's the surface. What's the region of integration, though? It's the thing on the ground. Remember, because this is a function of x and y, my domain is actually, get over there. My domain are the x's and y's that I plug in to get just that part of the surface. So looking at it from the top, I'm looking at how can you define this region on the ground? And polar, right? This is polar. This is great for polar coordinates. So in order for me to do this easily, I'm going to take this double integral and I'm going to convert it to a polar integral. So I'm going to make a change of coordinates. Now, you might be saying, wait a minute, you just told me that we didn't have to look at it as spherical and do that whole thing a second ago, right? The reason I said that is because we had defined the sphere as a vector function. A vector function. This is what we're doing right now is we're saying we have a special case where our z is a function of x and y, and therefore we won't look at it like a vector function. We're not going to use the same thing. It's a special case. So I'm going to convert over to polar. I'm looking at this region on the ground. Here it is. It was radius 3 and radius 1, right? I'm trying to find this stuff in here. So what would be my conversion here? Theta and r? Is that what we used? Can you tell me what theta is between? 0 to pi. Can you tell me the restriction on r? 1 to 3. And now what we need to do is we need to convert all our variables over. All our x's become, how does it work for polar? X becomes r cosine theta. All our y's become r sine theta, right? And then you always have to put the r and then dr d theta, right? So I'm going to convert this integral now to polar. I'll go 0 to 2 pi. It doesn't matter what order I go here. 1 to 3. Doesn't matter because they're both constants, right? Square root of, anybody see what that becomes? Plus 4r squared. 1 plus 4r squared. Because if you factor out a 4 out of the last two terms, you get 4 and then in parentheses x squared plus y squared, but x squared plus y squared is r squared by the Pythagorean identity. And then the very important r from polar conversion, and now dr d theta. I'm not going to work this the rest of the way, but you can see that this would be a basic substitution, right? Do you all see the basic substitution in there? U would be 1 plus 4r squared. Du would be, well, you have du out there, right? Can I trust that you would take that and be okay with that? Okay. Okay, let's move on. Maybe not. That's it for 13.6. Is that it for 13.6? I guess so. I thought there was more. Let me just check something here. Yeah, that's all. So what about some homework out of there? Nah. No. You want the practice. I know you want the practice. I sense it. I can feel it. So for 13.6, this is coming off of page 805. I think what would be valuable to you would be for you to find some equations of planes, like do one of those and then do one surface area. So let me just see here. Find the equation of the tangent plane to something like maybe, it actually starts on page 806. Maybe number like 29, 31. Those are like find the equation of the plane. And then 36. $39. Yeah, that'll work. All right, we have exactly 3 more sections left in the book. And we'll see how much I get through this one. I know we won't finish 13.7 today. 13.9 is going to go very quick. 13.9, when we get to 13.9, it's going to take us 15 minutes. It's not a very long section. So this is the last real big section. 13.7, there's a lot here, okay? Oh, not 13.7 calculators. Aren't y'all happy? Settle down, please. I'm excited for you. We're gonna finish the book. All right. The whole idea behind talking about the section with surfaces, and then you doing that handout, or we doing that handout in class the other day, is so that we can attack this section, 13.7. The whole area thing, surface area and tangent plane, was just a consequence of us looking at surfaces. But now we see what we're going to do with it. So surface integrals. I mean, if you think about everything we've done. I mean, we've integrated over curves, right? We had the idea. I'm going to draw these. Well, I guess I'll put them on our thing here. If you go back to like just Cal 2, right? When we integrated, we were integrating with respect to x, right? So we could look at this as having integrated over that little interval, right? We integrated a curve over an interval of time or something, right? And we've done in this class where we can be 3-dimensional, and that curve can be doing whatever, and we can integrate over that curve, right? Call them line integrals. And then if for some reason you had a vector field in this space also, then we had this concept of work, right, as you're trying to move points through the vector field. But it's basically the idea has been line integrals. We're integrating over lines. Now, we did do some double integrals, right? Double integrals, when we did double integrals, we were integrating like a surface up here, and we were integrating over some region on the ground, right? We just did one of those. So if you look at it this way, we are integrating over a region on the ground, though. You see that? Here we're integrating over a line. Surface integrals is we're going to be trying to integrate over a surface. So it's a little confusing, but you know the little part, the dx, the dA, right? The d little s, right? These have all meant something before, right? This meant dx, little infinitesimal length. dA was an infinitesimal area, right? ds was arc length. dr, remember that one? Was like with respect to a vector, like a tangent type vector. Now what we're going to do is we're going to be integrating where we have d capital S. So the infinitesimal that we have on the outside that we're integrating with respect to is well, what's capital S? It's a surface area. We're integrating with respect to surface area, which is where this whole idea of surface integrals comes from. Moving along a surface, integrating over it as you move through it. So that's the definition. Given a scalar function, we start with scalar functions, then we'll get to vector functions. If you're given a scalar function on a surface S with the vector equation of the surface given by this, so we have the parametric representation of the surface, and we have the u and v are restricted in some domain, then the double integral over S, over the surface of the vector function, with respect to the surface is the double integral over d of f of ruv. What the heck is f of ruv again? What did that mean really for us? This was purely notation, right? It means you take the f function. For x, you plug in the x component of r. For y, you plug in the y component of r. And then for z, you plug in the z component of r. Then what is this right here? It's all this crap right here. That's surface area, right? Which is why that's ds. ds is your infinitesimal surface area. That is your infinitesimal surface area right there. If you go back and you say, and you look at where, when we just defined surface area, we said it was the it was a double integral of what, the magnitude of the cross products, dA. So that's just ds now for us. So how do we try and visualize this? It's not an easy visualization, all right? Which is why I'm not going to try and show you that right now. Okay. How in the world do I explain this? All right, well, let me explain it this way. Let's say we have a scalar function. I'll make one up. Let's say, and it's we'll make it three-dimensional. That's a three-dimensional scalar function, right? Now, if I'm in this room, let's say, and I say, what's the value of that function at the origin? Then you're saying what? F of 0, 0, 0, right? Which would be 0. Then, if I try and go from the origin to that projector with a straight line, I could call that straight line C, couldn't I? And then what I could do is I could say add up all the values of the function along that line. Are you with me or not? That is what we did in the previous sections. That is called a line integral of f ds. That's what that would be. What I'm doing is at every point in space, I'm finding the value of the function at each of those points. As I move across that line, I add them all up. That's this answer. Y'all follow that? The difference now is that I want to add up all the points not along that straight line, but along what? A surface. So imagine now, instead of going from the origin to that projector, I have some like surface out here, right? And it may or may not go to that projector. But let's just say one part of the surface touches the projector. What I'm trying to get you to do is add up all the values of the function all along that surface, the entire thing, until you get, part of it's in the projection. Add up all of those, and now give me that total. So you're integrating along a surface as opposed to integrating along a curve. Understand the difference? Okay. Maybe you do, maybe you don't. So let's try and figure out what the next thing is here. This is an example. So find the surface integral of x, y, z. That's the function I was just talking about, where s is the part of the unit sphere above the cone, z equals the square root of x squared plus y squared. So just like I said, you have, sitting in three-dimensional space, a surface. Here it is. I have a cone. I have a sphere. I want the part of the sphere above the cone. So above the cone, but on the sphere. So do y'all see it's that red little cap there? So imagine going to that red cap. That red cap, at every point on that red cap, right, have an x, y, and z. Yes? Plug it into the function, compute the answer, save it. Move to the next point, do the same thing. Next point, do the same thing. Do all those along the entire surface, add them all up. What's the number? Well, that's the surface integral. Okay, it's going to take that infinite sum. So our challenge in this problem is really, when you look at the formula, our challenge is going to be very similar to what it was before. It's the computation of this. Yes? It's this computation. Plugging stuff into the function shouldn't be that much of an issue. Well, of course, we'll have to still integrate it, which will suck, but, Okay, so let's see if we can do this. I'm going to leave the picture up there because I want you to help me. How are you going to define capital S? Like, how are you going? You've got to come up with the vector function that draws capital S. And not only does it have to draw it, it can only draw just capital S. It can't draw the whole frickin' sphere. We want just the cap. Right? Now, the fact that the red cap is a part of the sphere makes you think you should probably use the vector function that we used before to draw that, right? But you can't just let U and V be what they were before, right? So somebody tell me how I can draw that red cap. Remember, my phi, well, not phi for us. What were we using instead of phi? Was it U? So our U, this way, cannot be 0 to pi. It's got to be 0 to something, right? 0 to something. And then, can I spin all the way around? Yes. So I want to vary my U by something. I'm not sure what. And I want to be able to spin around the entire way. And if I do that, and I fix my radius here at 1, right? Then I should draw that cap, shouldn't I? Do I follow that? So how are you going to find the restriction, though? There was one like this for your take-home, right? I told you to do the problem in spherical coordinates. And this is, you were supposed to approach it the same sort of way. You had to figure out what this angle was. So let me do it the way I don't know. Go ahead. Mm-hmm. Mm-hmm. Exactly. So imagine taking this sphere thing and cutting it in half and looking at a cross section of it. That's the best way to get that angle. You've got your cone coming up through here like this, right? Now what was the equation of the cone? It was z is equal to square root of x squared plus y squared, right? And this is a unit sphere. What's the equation of a unit sphere? X squared plus y squared plus z squared equals 1, right? So I'm looking at a cross section here. Now when I look at a cross section, that means one of the variables is what? 0. So it's either the x or the y, right? Depending on how you want to cut it. You following me? I'm smashing myself onto the xz plane or the xy plane. Your choice. What do you want? Doesn't matter. You want this to be the xy plane? Or xz plane, sorry. Z is going to be up and down. Z is going to be up and down. So what I've done is I've come to this picture, and if this is the x-axis coming out towards us, I'm cutting it this way. With the plane parallel to the xz axis, I'm peeling it open, right? Which means y is what? 0. So this means y is 0. And now I want you to rewrite both equations again. What would you get? Z is equal to x, or absolute value of x. And then the other one would be what? Z squared equals 1 minus x squared. Yes? But look at this one right here, z equals x. That's all we need right there. That's the only thing we need. Why? That tells me that the slope of this line is what? 1, 1, 1, right? So the ratio is 1, 1, which means it's got to be 45 degrees. Right? Yes? Which means that the u variable, which is like my phi was, remember the u is measured from here to here, isn't it? So that would be pi over 4. Right? 45 degrees. So what I'll do is I'll let that u variable vary between 0 and pi over 4. I'll let my v variable, which is like the theta, spin all the way around, and that should draw that whole cap. With me? Okay, that's it. I mean, that's the setup. Now you still have to find everything else. So here's what we've got. We've got the double integral over s of f of x, y, z with respect to surface area is equal to, this is turning into double integral over d, where d is the restriction on my variables that draw s. Okay, so notice I'm changing from s to d because s is saying, hey, it's the surface. This is saying d is the restriction on u and v that draw s. And then I have here f of r of uv, and then magnitude of r, partial r with respect to u, partial r with respect to v, dA. So that's just the formula, right? What is our vector function? Well, it's the one that draws the sphere. So we've used this now, what's the third or fourth time we've used this today? But our restrictions are that our v can go between 0 and 2 pi, but our u has to be between 0 and pi over 4. So I need to figure out what the magnitude of r cross v is, or the magnitude of the cross product of those partials. We did that already, didn't we? And it came out to be sine u? Was it sine u or sine v? There it is. It was sine u, wasn't it? Look, do y'all see that we've already done, like this part right here, we did this earlier? All that freaking work we had to do for it, and we got sine u, right? That's why I'm using the same example so we don't have to redevelop everything again. All right, so that's going to be sine u, but I need to figure out what the function evaluated at this vector function is. So the function given to us in the problem was what? I'll just put it on the side here. F, that's basically the integrand. What's the integrand? X, Y, Z? Wasn't that it? Look at the integrand here, X, Y, Z, right? So what I'll do now is I will imagine replacing the X with what? The X component of my vector function that draws my surface. Changing the Y with the Y component, and then changing the Z with the Z component. So we have double integral. I'll go ahead and put my restrictions on U and V right now. 0 to 2 pi, 0 to pi over 4. My function evaluated. So it's what? Sine U cosine V times sine U sine V times cosine U. So again, this is X, Y, Z, right? X times Y times Z right there, which comes from this. And then what? This yellow part, which is sine U. And then dA, which is for us, make sure we get this right over here. It was dV du. Oh no, du dV. And I believe we can combine some of this together, but we don't get any good Pythagorean identity stuff, do we? It's just going to be what? Sine squared U. Oh, sorry, I forgot about that one. Yeah. So we'll have all this stuff. It'll be sine cubed u, cosine. So let me put cosine u, cosine v, like that. Double integral. I won't rewrite everything. Is that everything? Sine v. I knew I was missing something else. Sine v. D u dv. And since these are constants, you could actually separate this into two different integrals and multiply them, because our u's and v's are separated from each other. But you could also do it all at one time. If I did this antiderivative with respect to u, this is a basic substitution. U is u. Well, can't use u. Our substitution would be to replace sine u with some variable like, let's say, w. W is sine u. This is w cubed dw. So it would work out nice. And then this one, antiderivative of that with respect to v, is pretty clean also. So we could do this. Not going to, but we could. All right. Questions? Some applications of surface integrals of f over s. Oh, wait a minute, hold on. I gave you how to do that problem. That's take home, right? The one with the integral, that one's hasn't been turned in yet, right? The one I said do the problem with spherical. I force you. No, I'm not saying the bonus one. Your last mini take home quiz that hasn't been turned in. That problem has that one with the cone, right? Doesn't it? Okay, whatever. I may have just like revealed how to do that problem to you, which is good. I mean, the approach is there. All right, so look, some of the applications. So think about what I was saying again. If you're moving along a surface and you're trying to find the value of some function at every point on its surface, and then adding them all up, then if you have some definition of what's happening there, that sum might mean something. For example, if we take the density, right? The density at each point, so we integrate the density function along the entire surface, then we're going to get the mass of the surface. We did that before. It's the same thing when we had like a curve. We take the density, each point, density function, and that gives us the mass. And if you know the mass, then you can find center of mass. So you can find the x bar, y bar, z bar that gives you the center of mass of a surface, three-dimensional surface. Understand? I'm not going to do any of these, but that's just some of the applications. I think this is a good time to end. We'll come back and do the special cases. Now, we still have a long way to go in here, because we have to do, this is starting to look familiar now. Look, we're going to find the surface integral along here. So now what we'll do is, instead of saying just add up all the values along that surface, do it along this surface, and the back surface, and give me the total. And then later on we say, now, this is all still part of the same section. Now imagine you have a vector field. And so at this little patch, at every point on that patch, there's vectors from the vector field. And so what we're going to try and do is compute somehow some measurement of how much is coming out of that patch. That's what we're going to do next week. We'll try and measure how much is coming out of this patch for that given vector field, and we call that the flux. And what we do is we add it up along the entire surface, and that's the total flux on the entire surface, which is like magnetic fields, things like that. So physics applications. Flux, flux, flux. See, this is a long section. Okay, get out of here. Have a good Thanksgiving.